Today we are going to solve some tutorial problems. These are the problems associated with both the first law of thermodynamics and second law of thermodynamics. We will go over some multiple choice problems, some short answer type problems to get a feel of how to answer certain kind of questions, and also hopefully it will clear your concepts on these two particular topics, because after that we are going to move it to a different one from next module itself. So, therefore, we will go over this one. So, we will start with some multiple choice questions based on the first law. So, multiple choice questions, the first one is work done in a constant volume process is either negative, 0, positive or none of the above. So, work done in a constant volume process is where your volume does not change, and if you remember, the definition of work done is dW equal to minus PdV. So, it is always, that is the formula. So, we have to see the change in volume in order to see the work done. Since we said that it is a constant volume process, which means the dV equal to 0. If dV equal to 0, then the work done will be 0. So, 0 will be the answer to the question. So, you whenever you are looking at this, you should pause the movie, think about the answer, and then you can actually see what the right answer is, and that way it will be helpful for you to probably get the concept across. Second question, by convention work done on the system is negative, positive, 0 and none of the above. So, this is a question based on totally memory or the concept of the particular law. So, we have discussed that always we are going to take conventionally work done on the system as positive. The reason is, as we have discussed before, first law of thermodynamics is du equal to dq plus dw. Now, when the dq is 0, then internal energy is equal to the work done. Now, you know that when work is done on the system, the internal energy of the system increases. So, therefore, if work done is positive, then internal energy will be also positive. That is why conventionally work done on the system is always positive. And you can see from the above expression also that if work done on the system happens, then typically dV is a negative quantity, because volume decreases. In that case, minus P dV is a positive quantity. So, therefore, this way also you can see that work done on the system is positive. So, positive is the right answer. Which of the following is not a path function? Heat, kinetic energy, work and internal energy. So, as we have discussed, heat is a path function, because heat can be changed by either constant volume or constant pressure process. Work is of course a path function, because one can do, we have already shown by by graphical ways also that work can be done in one step and multi step. So, therefore, work is also a path function, because it depends how you are doing the work. Kinetic energy is a little bit tricky one. You might think that it is energy and therefore, it will be a state function. However, kinetic energy is nothing but kinetic energy is proportional to mass and velocity square. Now, mass is of course intrinsic to the system. However, a system can go from one step to another step using different velocities. It can be faster and then slower, or it can be slower and then faster. So, however, at every point that kinetic energy can be different. Internal energy, however, by definition is a state function, because internal energy is governed by the specific system coordinates. For example, we showed that internal energy depends on atom number of molecules, volume, temperature and things like that. So, therefore, it can have therefore, it is by definition is a state function. So, this is the right answer. Total energy in enthalpy for a cyclic process is 0. Double the initial enthalpy, initial state enthalpy is constant or none of the above. So, in a cyclic, when you are talking about a cyclic process, which means that we start from somewhere, let us say start from A, and we do whatever we want to, and we come back to the same state. Now, this question actually is slightly twisted in the sense that whenever you talk about a cyclic process, the state functions are going to be always 0. Change in the values of the state functions are going to be 0, because state functions depend on the state of the system and not the path. So, therefore, whichever path it takes, it does not matter. If it comes back to the same place, state function value will be 0. Now, the question actually boils down to this particular thing: is enthalpy a state function or a path function? Now, we know by definition that enthalpy is nothing but heat at a constant pressure. Whenever we say that heat at a constant pressure, it automatically we are defining the path. So, therefore, enthalpy is a state function, just like other thermodynamic potentials. Since enthalpy is a state function, therefore, for a cyclic process the change will be equal to 0. Next question: work done is 0 for the following process: constant volume, free expansion, first and second, and none of the above. Anyway, so the question now again asking you two things: is constant volume work done is 0? Yes, we have explained that in previous questions. And free expansion case, what is the work done in free expansion? You remember that for free expansion dW is, or for any case, the definition of work is integration of this particular quantity. Work done for going from one step to another step is minus P external dV. It is the external pressure against which the system expands or contract, giving rise to some work done. Now, in case of free expansion, as we discussed before, external pressure is 0, because let us say the gases are in a particular chamber and there is a barrier here, and suddenly if we create a hole, then the particles will diffuse to the other side. It will diffuse to the other side against any pressure. So, P external is 0 for a free expansion, and therefore, that will also be 0. So, work done will be 0 for both constant volume case and free expansion case. So, sixth question: according to the first law of thermodynamics, total energy of the system is constant, heat changes to work completely, internal energy does not change, and none of the above. Now, first law of thermodynamics is the law of conservation of energy. So, therefore, it says that the total energy of the system will always remain constant. So, therefore, one is always right. Second one, heat changes to work completely, it is not true, because you know that the internal energy is equal to change in heat plus change in work or work done. So, therefore, heat cannot change, because there are some processes in which internal energy of the system will change. So, this second one cannot be true, and internal energy that does not change is not true, because internal energy may or may not change depending on whether there are processes in which it may change or may not change. For ideal gas, we know that if temperature does not change, then internal energy will not change. However, that is not true for other systems. So, seventh question: compressed air coming out of a punctured football becomes cooler, becomes hotter, does not change, and attains the atmospheric temperature. So, although we know that the air inside the football is actually a real gas and not an ideal gas, however, we can understand this kind of questions, or which are little bit conceptual questions, we can understand by taking an equivalent approach of ideal gas system, because real gas will be difficult. So, therefore, let us consider that if ideal gas were inside a football and if it came out, what would have happened? Now, immediately you can see that there is an expansion in volume. It was compressed, therefore, it was in a smaller volume, and it is coming out and in bigger volume, and therefore, and since we know that the pressure after coming out is actually decreasing, because it was in a high pressure before, you have to pump the football, right, with a pump, you have to push the air inside. So, the pressure is more than 1 atmosphere for sure. So, when it is coming out, the pressure decreases, and therefore, since P is proportional to temperature, therefore, temperature also will decrease and the air will become cooler. So, eighth question: work done for the process P v equal to K, or K is a constant, is 0, P V2 minus V1, and then third option is P1 V1 ln V2 by V1. Here P1 means the initial pressure and V1 means initial volume. Similarly, V2 means final volume and things like that, and none of the above. So, to understand that, let us just calculate the work done. So, what is work done? So, dW we can write as minus PdV. So, now we know that we are going from initial point to the final point. Here also we are going from initial point to the final point. Now, initial point pressure is P1, volume is V1, final point pressure is P2 and volume is V2, which means that at any point along the whole chain it is nothing but PV. So, therefore, we can take the P as P equal to P1 V1 by V, where P1 and V1 are actually fixed points, right, they are constants P1, V1, P2, V2, they are all constants. Now, let us replace P, which is a variable, V is also a variable, whereas P1, V1 are constants in this equation. What will you get is that P1 V1 dV by V going from V1 to V2, which means we are going to get minus P1 V1 ln V2 by V1. So, here it looks like the third option will be correct if I put a minus sign, other options will not be correct. You can think about the case where the second option will be correct, because you talked about where the 0 will be correct. The second option will be correct if it is done at a constant pressure. However, let us put it at P2 and minus. In that case, if it is a constant pressure process, then the second option will be correct. Okay, continuing that, let us talk about the ninth question. In an adiabatic reversible expansion of an ideal gas. So, it is an adiabatic process, it is a reversible process and it is an expansion process. You have to think about all the three things. Temperature increases, temperature decreases, temperature remains constant, and it is not possible to know. Now, it is possible to know because it is an ideal gas. So, we know all different types of calculations of an ideal gas, and it is an adiabatic process, and we know that in adiabatic process our dq equal to 0. So, therefore, from first law of thermodynamics we know du equal to dw, that means change in the internal energy is equal to work done. It is an expansion process, and we know that expansion process dw is minus p dv. Expansion process means dv means volume increases, therefore, dw is a negative quantity, and if dw is du is a negative quantity, if du is a negative quantity, we know du equal to cv dt, and cv is a constant and that is a negative quantity cv dt. So, therefore, dt must be a negative quantity, and you know what it means that dt is negative quantity. It means that the final temperature is less than the initial temperature, therefore, the change in temperature is lesser, negative. So, temperature decreases is the right answer. 10th question, in the free expansion of a real gas in an isolated chamber, okay, what will happen any of these four things. So, there is a catch here. So, you have to see the real gas, that is a catch. So, free expansion as we discussed before, free expansion of an ideal gas is in an isolated chamber, temperature remains constant. The reason is that in an isolated chamber your dq equal to be 0. So, du equal to dw, right. So, when it is a free expansion your work done is also 0, therefore, du will remain 0, therefore, temperature will not change for an ideal gas. So, for an ideal gas, here the question is about real gas. However, we are talking about ideal gas just to get a premise for understanding this particular thing. So, for an ideal gas, as you can see, the dq is 0, dw is also 0 because it is free expansion, therefore, du will be 0 and therefore, dt also will be 0, temperature will not change. However, real gas is not the case, and the reason is I will explain. In case of real gas, however, what happens is that initially the particles were close together, and then when the expansion happens they become far separated. So, these particles overcome the attractive interaction between them, and therefore, the system does some work, and therefore, because the system does some work, the dw becomes negative, and therefore, du also become negative, decreasing the temperature of the system. So, temperature decreases is the right answer. However, there is no option like that. So, energy will not decrease because it is an isolated system, temperature increases is wrong because temperature decreases we know, but there is no option like that. Therefore, the right answer is that pressure decreases, because whenever there is an expansion in volume the pressure decreases. because pressure is inversely proportional to the volume. Of course, for the ideal gas, but also for real gas it may not be exactly inverse, but of course it is reciprocal. That means, if pressure increases, volume decreases, if volume increases, pressure decreases. Question number 11. If a system is heated up with volume being fixed, what are the things that is going on? The work done is positive, the work done is 0, the work done is negative, and internal energy is negative. Now, if a system is heated up with volume keeping fixed, that is the idea. So, you are putting heat to the system and the volume you are not allowing to change, which means your work done is 0, because there is no volume change, means we already discussed that work done will be 0, which means your du is nothing but dq. And is dq positive? Yes, because we are heating up the system, we are putting heat to the system. So, therefore, your internal energy has to increase. So, change in energy is negative is wrong, because it will be positive. So, work done is negative, we have already discussed that if volume is fixed, then there is no work done. The work done is 0 is the right answer, therefore, and work done is positive again is wrong. 12th question. How do we calculate the change in energy for an irreversible process? By calculating reversible path between initial and final state, cannot calculate, by calculating the potential and kinetic energy, and by assuming the process to be reversible and applying standard formula. Now, this is a trick question, because whether the energy of the system is property of the state of the system. So, if we know the kinetic energy and potential energy of the system, we can always calculate the total energy of the system or change in energy of the system. We need not really look into the path, because the internal energy. So, by change in energy, by that we mean internal energy of the system. It does not depend on the path. So, therefore, it does not matter which path it took, we just need to know the final value and the initial value, and it will be all right. So, by calculating the potential energy and kinetic energy will be the right answer. Okay. Question number 13. Reversible work done by the system is maximum compared to the corresponding irreversible work, minimum compared to the corresponding irreversible work, cannot say with certainty, and maximum minimum depending on it is done isothermally. So, I will remind you again that how we calculate the work done for two processes. Let us say we are talking about work done by the system. So, work done by the system is typically an expansion work. We start from 1 and go to 2. If it is done in one step, the work done will be this much, and we have discussed that if you do it in 2-step process, then let us say you come here and then work done by of the system will be this much. So, let us say you come here, so it will be this much, and then finally, if you do in a multiple step process, then it will be all the area under the curve. So, therefore, it is maximum compared to the irreversible work. Which of the following definitions best describe the concept of work? Flow of energy due to temperature difference, flow of energy due to uniform molecular motion, the random motion of molecule, and all the above. Now, what is work? Work is unlike heat, work has certain direction. For example, if it is an expansion going from a smaller volume to larger volume, then the molecule is going to move in a particular uniform directions. If it is heat, then when you increase a little bit more heat into the system, molecules motions will be more random. It will be jumping with higher vigor when the heat is inserted into the system. However, if it is work, then the molecules has to move in a certain directions in order to expand the system from one size to another size. So, therefore, I would go with this answer, that flow of energy due to uniform molecular motion. And flow of energy due to temperature difference, again that is called heat, right. So, when you do that, due to temperature difference, we know that heat flows, and depending on whether talking about solid system or gas systems, the flow of heat will be different. Okay, question number 15. What state function must remain constant in the Joule experiment? And question B is, what state function must remain constant in the Joule Thomson experiment. This is an easy question. You know that in Joule's experiment the internal energy remains constant, and Joule-Thomson experiment the enthalpy remains constant. So, let us see, A u and B h will be the right answer, but let us see the other options. Yeah, the second option is wrong and the other options are also wrong. So, now we have finished the multiple choice questions for the first law. Now, coming to the multiple choice questions for the second law. First question, the entropy of an isolated system can never increase, decrease or be 0. What does it mean? An isolated system is a system in which the heat cannot come from outside to inside, or it cannot go. However, an isolated system still can expand, just like our universe is an isolated system, it is still expanding. So, if it expands, we know that entropy can change. So, it can increase. Can it decrease, however? We have discussed this during the second law of thermodynamics, that an isolated system like our universe, for example, the entropy cannot go to 0, it cannot become lesser, it is always increases. Why? Because any spontaneous changes will increase the entropy, and any change which is reversible will not increase the entropy, but nothing will actually decrease. So, therefore, an entropy of an isolated system can never decrease is the right answer. Second question, entropy can be transferred to and from a system by which of the following forms, like heat transfer, volume change, both the above mentioned and none of the above mentioned. So, we know that entropy is proportional to the reversible change in heat divided by the temperature. Now, if you transfer a heat, let us say non-reversibly, will it change the entropy still? It turns out that of course, we can always define a path which is reversible, meaning we can always define a path by which a reversible change in heat will take place, and therefore, we can calculate the corresponding change in the heat when the process is done reversibly, and we can calculate and estimate the entropy. But if the volume change also takes place, will it change the entropy? Now, it turns out that indeed if the volume change happens, then also entropy will change. So, therefore, I will go with the above, that both of the above mentioned, because we will show that a change in the volume also will give rise to, and the reason is that imagine a situation in which the heat flow happens and the internal energy remains same, then the change in the heat also is correspondingly related to the change in work or work done, and work done also is related to the change in the volume. So, therefore, whenever there is a change in the volume, there is a possibility that entropy can change. Another example of change in entropy by volume is free expansion. For example, let us say the particles are there in one part of a bigger volume, and suddenly a partition is removed and the particles expand to the full volume. In that case, they occupy much larger area, and we will show you later on that that changes or that increases the entropy of the system. So, therefore, by changing both the volume and by changing heat, one can change the entropy to and fro from the system. Third question, which of the following is false? For a reversible process, the entropy generation is 0. The entropy generation does not depend on the path the system follows, and for an irreversible process, entropy generation is greater than 0. Now, let us understand each point. For a reversible process, entropy generation is 0. So, we know that to be true. For example, we talk about Carnot cycle done in a reversible manner, and then first step there is entropy increases. So, it does not mean that the entropy generation will be 0, but however, we are talking about here the entropy of the universe. Now, in a Carnot cycle, if it is done in a reversible manner, the change in the entropy of the system is equal to the negative of the change in the entropy of the universe. I will write delta S. So, therefore, the total change, so we should write the question that for a reversible process, total entropy generation, here we mean that the change in the total entropy. So, total entropy change will be 0 for a reversible process. So, therefore, this is true given that we are talking about total entropy. the entropy generation or the total entropy does not depend on the path it follows. Now, the thing is that if it is an irreversible path, then what will happen is that we have to construct a different path that is reversible and calculate the entropy. So, therefore, first of all, the first statement is right, second statement seems to be right as well, does not depend on the path that the system follows, meaning it is a state function, it is not a path function, it does not depend on the path.
True, but
for an irreversible process, entropy generation is greater than 0, and that is also true. So, all are true. So, I would say that the answer is none of the above. Next question, in an open system there is a transfer of which of the following quantity? Mass, energy, entropy and all the above mentioned. Now, you know that this is a simple problem, because it is by definition whenever you talk about open system, then there is a change in, of course, both mass and energy. Now, will the entropy also will change? Now, let us say we talk about in an open system. Now, there may or may not be change in entropy, it depends on the process. So, when you are talking about a particular system, it has a particular entropy, because entropy is a state function. An open system allows the change in mass, change in energy, and it will allow, of course, change in entropy, because even an isolated system allow change in entropy, right. So, I would say all the above mentioned. Which statement is correct? ds equal to dq by t. Now, you will be tempted to always write ds equal to dq by t, but no, it is not true. ds greater or equal to dq reversible by t, meaning if I write it like this, ds greater or equal to dq reversible by t, yes, I think that is no, that is not true, because we will discuss that, because this is the right one, ds equal to dq by t, dq reversible by t, and we can also write that ds greater or equal to dq by t, which means that whenever it is reversible the equality sign holds, whenever it is irreversible then the greater than sign will hold. So, this is right and this is right, however, that is not right. So, therefore, third option is the right one. So, this is, so if you do not pay attention, there might be mistakes in this kind of questions, as I was just about to make. The entropy is a state function is true, is it always? Never, depending on whether the process is reversible or not, only when the temperature is constant. Since we talk about entropy ds is dq reversible by t, and there is only one reversible path, therefore, entropy is always a state function, and option 1 is right. Continuing with the multiple choice question, efficiency of a heat engine is defined by, this is very important to remember, that it is always work output by heat input. So, option 2 is right. The free expansion of an ideal gas in an isolated chamber, what will happen in the free expansion of an ideal gas in an isolated chamber, or for the free expansion of an ideal gas in an isolated chamber? Entropy increases, entropy decreases, entropy remains constant, and no comments. So, of course, will be entropy increases will be the right answer, because it is free expansion, it will fill the volume. Heat is transferred from A to B, which is true. Entropy of A decreases in the process. This is a good question, because you see what happens is that this question typically tells you that that the sub part of a combined system A and B, sub part may lose entropy. However, overall there will be an increase in entropy. For example, we will talk about A and we will talk about B. Now, heat is transferred from A to B. What happens in this process is that A is losing heat. So, A is losing entropy, and B is getting heat. So, B is gaining entropy. Now, when you add the gain and the loss, there will be an overall gain. So, I would say that entropy of A decreases in the process, that is the right one, entropy of B increases in the process, that is right one, entropy of a combined system increases, that is also right one. Next question, how do we calculate change in entropy for an irreversible process? By calculating reversible path between initial and final states, cannot calculate, by calculating the potential and kinetic energy of each and every particle, and none of the above. This is a very important thing for you to remember, is that entropy is a state function, therefore, it has to be associated with some state variables. Now, if I talk about an irreversible process going from A to B, there can be many irreversible paths. However, entropy of B has to be some specific value and A has to be some specific value. Therefore, change in entropy between A to B has a very specific value, let us call it C. Now, which means that in order to get C, we need a very specific way to change from A to B, and that specific way is a particular reversible path for which we can calculate. So, it is a specific path which is a reversible path, and therefore, we will be able to calculate the reversible change in heat, and by definition entropy is reversible change in heat by temperature, and we will be able to estimate the value of entropy even though we are using a very different path. I can give an example. Let us take I think we have talked about that, but I will still mention it here. Let us say that we are talking about free expansion of gas. So, what happens is that whenever you make a hole here, the gas will expand and fill the whole volume. This is an irreversible process. How do we estimate the entropy? We go from same half or same unfilled box to a filled box by using a reversible path. We can do it reversible by expanding this volume very slowly, let us say under pressure, and finally, we can reach this particular state B, and therefore, we will be able to estimate change in the reversible heat and therefore, change in entropy. So, the right answer to this question is that by creating a reversible path between the initial and final states. Question 13, in the event of water flowing from high to low in an isolated system, what will happen? In an isolated system, remember that is the key. Energy decreases? No, it is not possible because it is an isolated system. So, energy is conserved. Entropy increases, we will come back to that. Depends upon the amount of water? No, cannot say. We can still say, the thing is that whenever water flows from high to low in an isolated system, it is a very spontaneous process. So, it is flowing, water flowing from high to low is a spontaneous process, just like heat transfer from high temperature to low temperature. So, therefore, I will go with the entropy increases because energy is not driving the change. So, the change that is driven is basically the entropy. For example, when heat transfers from high temperature to low temperature, energy remains conserved because the total change in the energy is fixed, total change in the energy is 0. However, the process still happens and it happens due to entropy. Only those processes are possible in nature which would give an entropy dash for the system and the surrounding together. So, we know the system and surrounding together means entropy of the universe, and we know that those processes are possible in which entropy change of the universe are either 0 or positive. So, but it says increases, which is right, decreases not possible, remain constant possible. So, these two options are correct. Next question, if second law were not true, then a ship could be driven by extracting heat from the ocean. Run a power plant by extracting heat from the air. Both the above mentioned and none of the above mentioned. So, the idea is that second law of thermodynamics prohibits us to take the heat from the ocean and run a ship or extract the heat from the air, because it is only will serve one heat source, but in second law of thermodynamics we need one heat source and another heat sink working at two different temperature. So, which means that the engine could take heat from the ocean, but it has to throw the heat at a lower temperature. Now, where do you get the lower temperature? Because if we are in room temperature and taking heat from our room temperature reservoir, then something has to be cooler than the room temperature, and that is only possible by using a refrigerator to cool that. That means we have to use work to cool the system, and that will now drive the change of another engine. and if you combine them together the efficiency will be even lower. So, therefore, with one heat source or one heat sink it is not possible to run any engine, and therefore, unfortunately even though we have so much energy sources available around us, we are not going to just simply take the energy from the environment and do the work. So, therefore, we would say that if it were not true, then both we could have done both of the above mentioned, but it is not true. Next one, the correct sequence of the process taking place in a Carnot cycle is adiabatic, adiabatic, isothermal, isothermal, and we know the process. So, first is isothermal, then adiabatic, and then isothermal, and then adiabatic. So, this is a question that will test your knowledge whether you remember the Carnot cycle or not. Next one, example for reverse heat engine is heat pump, refrigerator, both the above mentioned and none of the above mentioned. So, I would say that both the above mentioned, because engine is where you take the heat and do the work and throw away some heat to the sink. This is sink, this is source. Refrigerator is just the opposite, where you take the heat and then take the heat from high temperature, you take the heat from the low temperature, do some work and throw the heat from to the high temperature. For example, you take the heat from inside of a refrigerator where the temperature is 4 degree Kelvin and throw the heat to room temperature where the temperature is, let us say, 30 degree centigrade, and you do that by doing some work, which is done of course by the refrigerator with the help of the electrical energy that makes the work, does the work. And the heat pump is also the same thing, where you put the heat from low temperature to high temperature.